of this is something I feel like if we set this mindset, grand mindset, then it will help us propel forward. So I'm a meteorologist, which means I was trained as a like a weatherman. That's why I put my title as from the weatherman's perspective. So I want to share with you this very long journey of technology advancement on up to today's weather forecast. Now, today, everybody can put out their phone and get instantaneous weather forecast information, very detailed, and looking out for next 7 days or 10 days, right? That's what our technology has led us to. So I want to bring you to this history of how this concept was formed. I want to introduce you Louis Richardson, who is a British mathematician and also a meteorologist. At the time, he wasn't really calling himself a meteorologist. He was basically a scientist. So in 1922, he published this book called Weather Prediction by Numerical Process. Now, by numerical, what it really means is equations. Now, the reason this book was revolutionary was because before that time, of course, people have been forecasting weather all around, right? Farmers, fishermen, or just everyday people, or astronomers. Everybody has an observational tendency. They can test the wind, they can watch the clouds, they can monitor the waves, and they can make predictions. And then every time they build some instincts and experience. But those are not numerical. Okay, if you are good, but your neighbor may not be as good as you, so your information cannot share. So what Richardson did was to derive a set of equations, and then he believes that by solving these equations, all these equations on the space, homogeneous space observation stations, then we can calculate through mathematics, calculus, to solve weather problems through math. Because basically, all our weather systems follow Newton's rule, follow physics. Okay, but the problem is that his idea was so advanced. Back in 1922, as World War I, there wasn't much technology, there wasn't much observation. So the European Center for Weather Forecasting produced a video of that. It's a little bit cartoonish, but I think it's easy to understand. So let's take a look about his story.
Louis Fry Richardson was an English physicist and mathematician, born in 1881. A prodigious talent, Richardson...
Oops, sorry. I was trying to increase the volume. Can you hear this?
Louis Fry Richardson
okay?
was an English physicist and mathematician, born in 1881. A prodigious talent, Richardson applied his scientific gifts to solve many problems throughout his life. At age 5, upon hearing his sister remark, "Money grows in the bank," he buried money in the garden to test this theory. When news of Titanic's sinking reached Richardson, he took to a rowing boat armed with a horn to experiment with the use of echolocation as a means to calculate the distance of an object at sea. Richardson's most famous work, however, was in the field of weather forecasting. A key element of modern accurate forecasting is the use of complex algorithms run on powerful supercomputers that process observations of current weather through a mathematical model of the atmosphere to forecast its future state. Meteorology in 1917, however, at a time when Richardson was deployed as an ambulance driver on the Western Front, relied on matching current weather with repeated patterns in past weather records. Richardson knew that a more scientific method could be applied, and while World War I continued around him, he began to experiment with the idea of creating a numerical weather forecast. For his first attempt, he tried to recreate a past forecast given for Central Europe, based on published weather data for that date, such as temperature, pressure, and wind speed. He devised a gridded map of the forecast area and generated by hand the first numerical weather prediction. These calculations took Richardson 6 weeks to complete, in which time he produced just a 6-hour forecast for one location. Whilst this first forecast was far from perfect due to limitations with the data used, Richardson's pioneering methodology was later found to be sound. In 1922, Richardson published the now famous weather prediction by numerical process. Alongside his methodology, he described his fantasy of what has since been dubbed his forecast factory. Richardson imagined a large circular theatre, like a hall, with a map of the world painted on its walls. He estimated that 64,000 computers, not computers as we know today, but mathematicians tasked with computing, would be needed to calculate weather forecasts in real time, each responsible for one small part of the globe. Richardson's foresight in this concept was phenomenal. His forecast factory almost perfectly mirrors how supercomputers now use parallel processors to undertake the huge numbers of calculations needed to run global forecast models. Whilst Richardson's vision of the forecast factory was never realized, he will be remembered as a pioneer in the field of numerical weather prediction, whose work set the foundation for modern forecasting.
All right, that's the story of him. What I found very remarkable is that he derived all these equations while at war. The reason he wasn't on the battlefield because he was a Quaker. Pretty much, he refused to take up guns and kill people. So he was assigned the ambulance job, and so while he had the time, he tried to develop science, which later on evolved into today's weather prediction model. So, but Richardson at the time faced two major challenges. And just what happened when you are so ahead of your time? One is computational burden, and then the second is the lack of accurate data, just not much data. So at the time, there was no modern computers. So when he thought about calculation, he thought about calculation by hand, mathematicians or a trained accountant, something like that. So he proposed to use a large group of human computers, and he believed we need 64,000 human computers to calculate weather forecast in time to make predictions. So the newspaper drew something like this, and then they didn't admire him. They actually were mocking him. They believed that this is so ridiculous that this artist found it ridiculous and ridiculous enough that they spend so much time drawing this and posting on the newspaper just to laugh at it, saying things cannot be done, because nobody at the time could have imagined that there would be the computer that we know today. So, yes. Any question? Okay, I'll continue.
Hà Nội
right.
hả?
Oh,
Ủa
there's
nãy
a question.
Thái nó kêu lên rồi giờ tới em hả?
Hello, please don't forget to mute your microphone. Yes, Simon, please continue. Simon, please continue. Maybe some guy mute your microphone, Simon. Hello, Simon.
Okay.
Yeah, come back.
All right. Okay. I guess somebody mute me. All right. Sure. Wait. Okay. Okay. Can we see the full screen again?
Yes.
All right. Thank you. Thank you. Well, so these are the human computers at the time. I mean, if you want to compute something big, this is how you set up your so-called computer. It's basically a factory, right? A man and woman, they are good at numbers. they calculate one set and they pass on to each other. So because you calculate one set of equation, you pass on your result to the next one passed down to the next, like that. So it wasn't possible by human until near the end of World War II in 1945. The U.S. Army funded a project in Princeton University, which led to this what's regarded as the first operational computer. It's called ENIAC. ENIAC. It's basically a whole room of machines with cables linking together, looking like this. And you see all this paper. These are paper trail of a punch cards. There's no keyboard. You have to type punch hole in the car, and you feed the program into something like this. Okay, it has the power of a modern day handheld computer like this, pretty much. Okay, so that's the power of computation electronically that was invented in 1945. However, simple at the time, it was advanced enough for a group of very talented scientists to put Richardson's equations into something that can produce numerical weather forecast. You can see this in this paper. They show some weather patterns. You don't need to worry about what's there. It's just some weather patterns of pressure change at 14 days. So it's a 2 weeks prediction ahead. So essentially, they especially these two professors, they used the model, the first computer at the time, to convert these equations into weather forecasting. The model, because it was funded by U.S. Army, was initially invented a design for calculating projectiles, like cannons, large cannons, the projectiles. They want accurate projection of the projectile, of their weapon. So especially this person is a Professor Charney from MIT. He's the right guy. The reason he's the right guy is because he was a mathematician himself, but then he liked to apply his knowledge. And very different from most of the scientists that try to focus on details and sometimes get trapped by it. He's the one who said, let's relax a little bit. Okay, in the Thai language, let's go sabai a little bit. Don't worry about the whole set of equations. We don't need to worry about the small ones. If the number is too small, if the error is too small, let's get rid of that in the beginning so that the error doesn't grow into the equation and then they ruin your forecast. Just this simple concept, he simplified the equations enough so that the calculator or the computer at the time, this ENIAC, was able to calculate a large quantity of data and then produce the weather forecast. Well, 60 years later, today, the forecast model looks like this. Very fine scale, very advanced. And then this is what I zoomed in for Thailand. You can see we got wind pattern, we got moisture, and you can zoom out. It's basically a global model today. And this is something, if anyone is interested, I can show you the link. You can play it by yourself. It provides you real-time data, many different types of data, variables, all the different heights of winds and pressure and temperature, and also forecast. Okay, so basically 60 years later, you can see, actually 100 years later, you can see Richardson's concept came true. So it took that long. It took 100 years. It took 100 years for a concept to come into fruition. So ironically, I feel like, yeah, you can be very advanced, but sometimes we don't get to see our design come true because the technology was not ready yet. But I'm putting this out basically to say that, well, it's personal choice. But if we believe that something will happen and will improve human life, and we should still do it regardless of we can see the fruit or not, because many times it's just not the right time or we didn't have the right tool. Today's model can do a lot more. And I'm going to show you one example of how today's numerical weather model not only will give you weather forecast, it can also do air pollution, fire, ocean features, and CO2, and also even space weather. So the next clip is a incidental interview I got by a Thai professor, and where he was asking me about PM2.5 in Thailand, especially regarding the urban source versus the springtime burning source. So if you don't speak Thai like me, just indulge me. This is a very short video, but basically it's me telling him and him explaining to the audience that Bangkok, Thailand, still is the source, the major source of PM2.5, even to the north, not the other way around.
โซลูชันที่เราสร้างเนี่ยกระจายไปที่จังหวัดอื่นไม่ใช่จังหวัดอื่นส่งมาที่กรุงเทพนะจริงไหม
On this day, yes.
ในวันเนี้ยในเวลาเนี้ย
โอ้โห
Yeah, occasionally in springtime when they start to burn, yes, you do see burning, but when you can see burning, smoke is PM10.
I see
2.5 is
มันไอ้พวกที่อะไรต่างๆเนี่ยมันเป็นไอ้ PM ที่มันขนาดใหญ่ขึ้นแต่ 2.5 เนี่ยกำเนิดจากกรุงเทพโดยเฉพาะเรื่องภาคการขนส่งและ this is source and spread out
spread out
to neighbor province
all the way to the north because you can see the wind. The wind is from the south.
So it's อยุธยาชัยนาทนครสวรรค์พิษณุโลกขึ้นไปจนถึงใกล้ๆเชียงใหม่เลยมาจากกรุงเทพครับนี่แหละครับความรู้คือความจริงนะครับ Data วิทยาศาสตร์อาจารย์จำยับพูดถูกไหม Data ไม่ใช่ดราม่านะ
Yeah, this is real data. And that's real data, and we can even do the forecast of it. So modern technology has evolved that we just have to wait for the right tools, but not like idly waiting, but just, sometimes we can push. Well, next, I'm going to introduce you one of the books of this very popular author, Adam Grant, has written, which I believe it really fits today's talk. And the book I'm focusing on is his book's originals. And because the opening story is quite interesting. I'll talk about that later. So the first thing he mentioned is we need to challenge the default. Well, the talk I was given, the title is Embracing Technology, right? Embracing means technology evolves. Why do we have to embrace it? Because sometimes human being has the tendency of being at present in a comfort zones. We don't want to learn new things, or we don't even want to accept new things because they're gonna change the way we behave. And it is okay as long as we keep a mindset that we are in default mode. And there's a story in which in his book that he found, and then this is actually from a customer service agents in Google, and they try to find out productivity differences about workers. So they check all the workers who change their default browser from Internet Explorer, assuming they're using Windows system, to Firefox or Chrome. If they change the default browser to something else, those people tend to stay at the job longer and then were better. Right? Their performance was better. So this is simple psychological differences here. And if any of the audience here are managers, I recommend that you can do something similar like that, not to tag people, but to understand or even to encourage your team members, to try not to stay in default, just to change a little bit. Because if you embrace this mindset and the statistics, the data is showing you that those people who don't stay in the default mode, they tend to stay in the job longer. It's good for the company, and in addition to better performance. That's basically because people who tend to do that, they possess a willingness to question the default. And then when they find, it doesn't mean that people who use Internet Explorer is wrong. Maybe they like it, but those are hidden in the data, right? It's just like the people who seek better options, they usually will contribute more and longer to the company. Of course, there are many other things. I won't go the detail through that, but I just want to list it there toss it out for you to think about it. The second thing is balancing risk. There's always the risk and reward things. The way I usually communicate with people is like insurance. Do you buy it or do you not buy it, right? If you buy it, you risk, you pay money. But if you don't buy it, there's a risk. There's a certain percentage of you maybe crashing your car going to work, right? So that's just buy some insurance. Embrace procrastination, overthinking. It is a human tendency. It's just like our mood. It's actually very difficult to avoid. So we embrace it, not thinking as a wrong thing, but you have to communicate and then later on decide when is the right time to act. And then we have to generate many ideas and test them and fail. And then we have to test ideas strategically, not randomly. This is something more of a teamwork, and we need open-minded managers, employers, who can be open-minded, who can seek dissenting opinions. Yeah, they don't agree with the higher level people. And then, most importantly, if you sense that your division or your company, your section is stagnant, it probably is the time to reevaluate and change the culture. And here I want to stop and tell you another story. It is the US CIA story. Many of you today certainly know what Wikipedia is, but what for many of us, including myself, didn't know is that way before Wikipedia is a thing, it's a gain traction. This lady here, who later became the deputy director of CIA, when she was still a field agent, very young age, she was proposing what later became Intellipedia, which is an intelligence version of Wikipedia. They share among FBI, CIA, National Security Agency, something like that. Those militaries as well, and it didn't really happen. It took her about 20 years, and then she tried twice. The first time she was just braced aside, Miss Medina, and the second time she has climbed the ranks to higher ranks. But also there were two things happened in between these two times. When she proposed this very well functioning system today, in between those times, the world changes. You can see the first of all is the internet. Again, it's technology, and then an event, right, changes the mindset as well. September 11 terrorist attack, 911 set the alarm for better coordination between intelligence agencies. These things is like a public shared space among different agencies. And before that happens, they always just use fax machine or print out and mail it to different agent, and it's very time consuming. And then it's just very slow. So all this example told us one thing, that basically future takes time to arrive, and we don't know how long. So we just have to plow through it. But as long as we can keep the purpose, we can be patient, and then we can maintain perseverance, it will go on. Michelin Company, as I know, has been around 100 years. So it certainly has its share of growth and innovation. That also took a very long time. So I want to pause here and welcome any thoughts. And because my setup, I cannot really read individual comments. I will ask you to please just unmute yourself and speak up. Can you do that? So can anyone, I'm really hoping to learn from you, share whether or not your job requires you to seek advancement in tech. And if you so, what's the challenge you're facing then right now? Can we have some comments? Just unmute and speak up, please. No one?
No.
Okay, please. Anyone? If not, no worries, no worries. Please think about it, and we can talk about more together at the end. One last chance. No one? Please speak up. All right. Okay, I'll move forward then. I have another story. The next story, I'm not talking about myself, but I'm posting my so-called Google Scholar page because I'm a researcher. My job is to do research and fundamental research, and then we published. So in the next story, what I want to share with you is that it's okay to share our ideas. Now, usually in a company settings or in a defense settings, we are discouraged to share our ideas. Like our ideas is critical. But I have a different view, and many entrepreneurs also share a different view that ideas are worth sharing because number one, your idea might be wrong and you didn't know. You wouldn't know if you don't share it and get feedback. Number two, what really matters is not my idea, it's about how you execute them. I mean, and then make it successful. So, but because the unique job of academic researchers in the university, our job is to publish. And if you publish, the graph here is showing you that the more you publish, the more people cite you. So these are the citation numbers. Different people have different numbers. Some are a lot, some are not so much, but very focused. Myself has these numbers here. It means like so far the papers, the scientific papers that I have published has been cited more than 7,000 times, which means my research becomes somewhat useful in other people's research. And some works will be more important than others. Here is a H index. There's something they rank academic impact, which means 45 means there are 45 papers that has been cited at least 45 times. And then, or is 125 is the I10, which means more than 100 papers being cited more than 10 times. So it's just it's a matrix to kind of like measure how much your research has influenced the community. Okay, I can pull out my ego and say, oh, this is how important my work is. But my point here is that the more you share, actually, the more you grow. And so that which leads to the next story. And I am a military aircraft nerd. I really love military aviation. I hope some of you, at least some of you, share some passion of that. But if you don't know aircraft, just look at this aircraft. They look very strange. If you know, you know, right? This is called F117 Nighthawk. It's painted black because its primary mission is in the nighttime. And the reason this aircraft is so unique is it's a pioneering product and ranking from a very interesting story. Now, today, you can see most of the stealth fighter, which means they can evade radar detections. They look like this, very sleek. They can fly all year round. I mean, all in different time of the day. So they don't need to paint black. They can fly in daytime as well. They look like they are more agile. They fly faster. But this one was the original. So I want to talk about this story. This shape came from this concept, which is called hopeless diamond. It's a very interesting story because the aircraft you're looking at is United States Air Force. But the concept came from Soviet Union mathematicians. So in 1962, a Soviet mathematician, Dr. I don't know how to pronounce this name, Yevsenev, published a paper titled Methods of H waves in Physical Theory of Diffraction. If you are not in the field of science, even I, not in the field of physics, I found reading this title already dazzling. But what this guy did is to derive a set of equations. Remember Peterson? who derived this weather physics equations. He derived this electronic magnetic wave equations in his paper, because he believed that if you can design a shape of an object well enough following this principle, then you can deflect all the radar waves, making it invisible to radar. So the concept looks like this. We don't need to understand it. And then eventually, if you apply it to the aircraft, then you will deflect all the radar. Today, all the aircraft today, you can see that they not only just use the surface, the shape, they also use materials. But at the time, the shape is the only defense. So he published the paper in Russian. But in 1966, the CIA translate the work and then given it to U.S. Air Force. Actually, the CIA obtained the work, the paper, and the U.S. Air Force translated into English. And later on, almost 10 years later, when engineers at Lockheed Martin Skunk Works, is a very famous aircraft design team, they came across this paper, this translated paper. So one engineer, they studied this paper and believed that, hey, we can actually design the aircraft to minimize radar detection, essentially making it invisible to radar. Okay, that's the concept of a stealth fighter jet. So that was 1975. This was the year I was born, almost 50 years ago. Then the concept, through computer generation optimization, they came up with this shape, which they call hopeless diamond. It looks like a diamond. The reason the engineers called it hopeless is actually a name given by aerospace engineers, because they were tasked to fly this thing, to make it fly. And if you know anything about aerodynamics, you know this thing could not have flown at all. It's just not possible. But somehow, through a lot of wind tunnel and design, they made it work. So in 1977, this team, 2 years later, you see, they designed the prototype called Half Blue. It looks like this. It's completely built by wood, really just by wood. And they use it to test the radar echoes, the radar reflection rate. And they found out that it worked, actually worked. Radar couldn't detect this aircraft mainframe. The only thing radar detected at that time was the pilot's head. So it was a new problem to solve. And so later on, they have to coat, you put on more like a gold or some metal coating to the cockpit, so that the radar wave won't penetrate it and detect the pilot's head. And to this day, and then in 1981, the first Nighthawk made a maiden flight. It was test flown many times, and was successful. This aircraft incorporated this Russian scientist theories using flat angular surface to scatter radar waves. That's why it looks like this very strange feeling, very strange shape. And there's a side story too, that around 1980s, the so-called fly-by-wire technology has matured. Anyone who knows the fighter jet F-16, Thai Air Force has a F-16A as well. They will know that this was the first operational fighter jet that used the fly-by-wire system, which means compared to the aircraft before, which is completely mechanical, using cables or using hydraulic lines to drive the surface, they use electronic signals to do that. And the reason this is important is because now the aircraft can be designed to be very unstable. So normally, if the aircraft is unstable, human has a hard time controlling it. You have to constantly adjust it. But because now it's computerized, you can fly it in a very unstable shape or even a strange shape like this. So the flying is mostly done by computers. Okay. So in 1991, And ironically, it was also the first time this aircraft was sent to the first Gulf War. 2 aircraft bringing 4 bombs, 4 GPS bombs, was and set the opening stage in one night over Baghdad and destroying their radio stations. And then they set off the 1991 Gulf War. But then it was also the time when this Russian professor, Russian researcher, because the collapse of Soviet Union, he was introduced to United States. So he was actually shown to tour F-117, and then people told him that it is your design 30 years ago that led to this technology breakthrough. So he expressed a surprise that because his work was largely overlooked, nobody cared in the US and in the Soviet Union, but then he found a profound impact from such a utility in the US military. It's kind of like an enemy. You contribute to the enemy's weapons. So I just want to put up here what the computers look like in 1975. It looks like this, okay? It looks like this. And today, our phone, whichever phone, doesn't have to be iPhone, will have like 100 times, even 1,000 times more computing power than the 1975 supercomputer. And so today's stealth fighter jet has evolved to a huge bomber, or US Navy's drone version, which can take off and land on aircraft carrier without a pilot, and also F-35, which is the most modern jet so far in operation in many countries' air force. So today's computer and material advancement made it happen. So the 2020 computers, you can pretty much imagine it to be like this. So any ideas can spark change, but it really takes many hands, resources, and time, and the right tools to make it real. The true innovation is a shared journey and not a solo act. And we know that. Sometimes we just need a reminder when we face problems. And no matter you are the designer, engineer, or the managers, we have to constantly look out for the right tool and to act just like the F-117 story. I found this quote by Henry Ford very interesting. And this is the quote on some more of the business books, because they talk about the importance of marketing and market survey, but also the unimportance of it. If you want to be truly innovative, you cannot afford to care about marketing too much. So Henry Ford famously said that if he had asked people or consumers what they wanted at the time, they would have said faster horses. But we all know that he is the inventor of this operational and mass production car called Ford T1, and he made a fortune of it. Today, you can see Ford pickup trucks everywhere in Asia, and that's really what innovation led us to. So I want to reduce all this mindset to the first thing is to say yes to new things. When there's a new phone, new type of phone, right? Let's say yes, let's see what it does. A new AI system, ChatGPT, for example, say yes, and then see what it would give us, right? And then keep working on it. We don't accept it as perfect. We see any new thing as a progression that it will constantly evolve and you constantly improve. So I want to pause for the second time. Now I'm very curious because I was told that the audience come from all sectors of Michelin Corporation, and from sales to marketing to production, also to R&D. So any audience, any of you, have you or has your job seen an example of innovation taking shape? I really love to hear your experience. Any comments or questions for now? Please just unmute and speak up. Anyone? please directly unmute and speak up. I really welcome your comment.
Hello, Palamas speaking.
Yes, please. Thank you.
I work as a process engineer. My past work was concerning about chatbot development, but now I have seen potential of AI. Maybe in the near future they can replace my past work that I use spend time around 8 to 9 months. Maybe next AI will consume few minutes to get our information or document and generate answer to user quickly.
It is possible.
Yes.
But the rule of physics also apply to the rule of technology development. That it's a what they call it's offense and defense. So you are concerned about the offensive part of someone has a bad intention developing that, just like computer virus. So there's a hackers and there's a virus and there's engineers constantly battling on that. It doesn't mean that your concern won't come true. It is really true. I mean, AI can hack into your system. An AI hacker that has, AI can write codes, right? I use AI to also write codes and teach my students to write codes. So it can actually write better codes or hacking codes a lot faster. But then the same thing applies to the defensive side too. It can detect this hacking also faster. So it's actually a rising water level on the two tubes. They don't really lead each other too far because you only get one success try from either end, then the other one will counter like that. So you look back the virus things and then now the future, the AI things. I don't think the possibility will be as big as we fear about, because a lot of things are going on. So do you have any other follow-up comments on that?
Yes. Actually, I have some doubt when you mentioned about AI, and we have to deal with a group of students. I quite wonder how if most of the students try to use AI to generate some document, a paper in the same topic, and how do you judge or how do you find difference between that and how they add value to that AI? This is my doubt.
It is wonderful $1 million question, because my simplest answer is there's no way you can stop it. So what do we do? Now the answer becomes very detailed, right? Now if you are a teacher and your students are, let's say, before high school, kind of like a younger students, and you want to channel them to use the right tool, right, the right way. So, but you also know, well, ChatGPT is free. Google Gemini is free. Before GPT, people already use Google and Wikipedia, students, to do their homework. Now it's just a lot faster. So as educators, then we just have to challenge them. Now the way is actually going back to the more engaged ways. For example, students, if you ask them to test, well, before you might ask them to do computerized testing. Now you just have to come back to classroom, pen and pencil and paper. That's one way. The other one is, my way is just to kill all the reports. You just present it. If there are too many students can record their presentation showing just like what I'm doing right now. The truth is, like, they might still use AI if they're smart or sneaky enough to produce their report, but because they have to speak it like I'm doing right now, they have to force their brain to digest the information and then speak it out. For me, if they can do the work, I'm okay, because eventually it's the knowledge, how much knowledge they absorb. And there are different ways of solutions. It depends on if you are an engineering professor or the English professor or a social science professor. It's just, they all have different ways. I hope that kind of address your concern.
Yes, actually, it's a very good answer. As you mentioned, I think with the AI, most of people can generate the result or target, but how to use or present it is quite important. I try to compare to the real life, like if our sales team or any company try to use AI and ask how to increase the sales volume, or either the manufacturer ask how to make the best or better product. Most of the company are usually get the same, but how to use or present it or adapt it in real life is quite important. Thank you.
Thank you. My final concept, my philosophy is still encouraging them to use it, but the right way, because then they can use them to help in a lot of different ways, even not what I can imagine. All right, so thank you so much.
Thank you very much.
I'll just move on next. I'm actually starting to talk about my kind of interpretation and usage of this AI. It's not in a technological way like AI methodologies. I'm not a computer scientist, but I am a data analyst. So AI has helped me a lot. And because my area is climate science, which applies to many, many different sectors, and I'm increasingly optimistic that one day AI or large language model like ChatGPT can help us propagate our knowledge and data or information further. Here's one example. And before I'm going to talk about agricultural sectors, focus on Thailand. But let's go back to USA for now. Food security is what agricultural technology strikes for. The only reason agricultural technology keeps evolving is to secure our food supply. And in the USA, you can see this large area of corn fields. Now, these are not only corn fields, these are the rain-fed corn fields. So, and that means they depend on rainfall. There's no irrigation. And this background curve shows you the corn production, corn yields, starting from after World War II, then it start to come up like that. So this year after year after year. And this is primarily due to breeding technology and also farming practice improvement. So to this day, you can see that there's no end in sight. It looks like we're going to produce more and more corn. And for many of you who don't know what these corn are for, they don't feed people directly. They feed cows or cattle. Then we eat those cattle or we drink their milk. So they still feed us eventually. But what I want to highlight here is natural disaster. So if we tilt this advancement, now you can start to see that even though the technology still improves, but year after year, you can see some very dangerous years in which there was a natural disaster that caused significant drop of corn yields. Now, this didn't cause food shortage per se, but if you're a farmer, your economy is heavily affected, negatively affected. You lose money, basically. And these two events has been related to drought. And drought in the US, in the central US, has been something very difficult to predict. And when they happen, sometimes they happen very quickly and very strong. And then if they happen at the wrong time, like the harvesting time or the growing time, then you lose a lot of the crop. But the interesting thing is like this. Now, before 1990s, after 1998, you can see that there was still a lot of drought events. All these are drought events. So natural disaster, climate, basically. Climate can still reduce your yield a lot. But after that, things change. And that is because after that, the corn breeding technology has advanced a lot. They start to engage in molecular markers, testing, combining ability, and there's a lot of other things, those hybrid development. So you can think about maybe this part as a traditional breeding, which you can just do it in your garden. Now this part is more like a laboratory way, like a GMO things. And then the future part and the recent part is the genetic editing. So you can see that 2019, was still drought, but then there was no drop in cornfield. Okay, so I want to show this just to say that irrigation use, it's an engineering way, becomes the mitigator of this natural disaster in alongside the breeding. Okay. There a question or is just background noise? All right, let's go on. So the most recent the World Economic Forum calls for interconnected nature of climate risk. What they are saying is weather extremes, like a severe flooding, like what we recently seen in Thailand, in northern Thailand, or drought or other combined extreme events that they believe are the future threat. Then we need to deal with that. So I want to present here and share here as a case study I've been doing in the past year, and it concerns the cassava farm, especially in northeast Thailand here, in this area. And the reason I found that interesting and relevant to today's talk is because many parts, especially in the hilly part of northern Thailand, northeast Thailand, the cassava farm, they co-planted with rubber trees. And as far as I know, natural rubber still is a very important material to tire making. And that's probably why, Michelin has a very strong Southeast Asia presence. So I believe that climate informations, if it can help cassava farming or cassava yield, it could help rubber tree plantation as well. Even though I understand that rubber comes from other economical or economical reasons for their supply and demand as well. But let's just look at the climate information because this is something that hasn't been done before. Now, we all know that crop needs water, right? But during the monsoon season, the challenge for Southeast Asia is the rain comes from cellular type, or what we call it convective. This is we call convective cells. Every day is like that. Sometimes it's a bigger cells, sometimes it's smaller cells. But when it rains, it only rains in one area, right? And then missing the other area. Now, if your farm is here versus your farm is there, even though the weather forecast tells you it's 50%, you just don't know if you're gonna rain or not. And that is a basic challenge of it. So just like a stock market, now you can bet on one company, or you can bet on a big index, like the USA SP 500 index, NASDAQ, Dow Jones, something like that, big index. And because that captures the overall trend. So if we somehow can collect all the soil moisture data here, and then compare with the cassava yield in the red line, this is the data I was provided by the Cassava Association of Thailand. Now you can see that the soil moisture and cassava yield, they come hand in hand. They're very correlated. And in fact, the soil moisture I use here has a 6 months lead time. They are 6 months earlier than the annual cassava yield, which means if we can monitor soil moisture well, we can have some sort of prediction or predictive power for the cassava yield. Okay, and that's quite interesting. Furthermore, because of these global climate connections, and if you superimpose, if you plot the yield, which is blue line, alongside with ocean temperature in a tropical ocean, Pacific Ocean here, which is the green line, you can also see some form of significant correlations, anti-correlations, which means that somehow the ocean temperature changes here, which is a huge domain, okay? A lot of heat change or heat exchange as well in the atmosphere can affect soil moisture in Thailand, which affect yield, okay? And the reason is because, and this is what basically my study, my background as a meteorologist is that the global weather systems are all connected and they are primarily driven by ocean. Now, ocean is not constant. Ocean temperature can be sometimes very high here, and sometimes and also very cold here. and change vice versa like that. And because of this huge area of ocean heat variations, it will change weather system as well. You move the cloud from here to here, which change the circulation pattern, the wind to go up and down in different way. In this case, if you have a higher temperature, you can suppress wind air here, which will make it drier, right? Then the soil moisture dries up in a way, then the cassava didn't grow so well. And that gives you the explanation of this negative correlation that we are now seeing, okay, on that. And computer models, climate models can capture this and provide you a relatively good prediction for ocean. Not so much for the land, but for the ocean, yes. Then we can use that information to predict cassava yield, okay, over the large area. And alongside with Gasesa University in Thailand, we have published a paper pretty much employing the same concept and technology for oil palm. This is the paper we published in environmental research, saying how we could boost Thailand's palm oil yield with advanced seasonal predictions. Now, as you know, some of you know, southern Thailand has a lot of plantation of palm trees. When I drove around there, I also see a lot of rubber tree plantation as well. And you can see that this, you don't need to understand that, it's okay. But you are seeing global map, which means that even as small as Surat Thani province, where the palm, most of the oil palm were produced, was grown, that it has a connection to the entire world weather, especially the Pacific Ocean. Then we can predict that. So using AI and actually using ChatGPT as a platform, and with the data that Professor Bia from Gasesa University got for me, the government data, this is the whole nation, whole Thailand of cassava yields, which has a longer record. But the reason they were concerned is because last year, 2023, saw a drought-related production drop, yield drop by 20%. Now, the cassava farmers are usually poor. They're just not well because they grow cassava as a grow, leave, and forget type of crop. You don't need to pay too much attention. There's certainly no irrigation. So when there's a drought or any natural disaster, the yield will just drop like that. But it will affect not only the farmers' income, it also affect the starch mills, factories' income. There's a ripple effect affecting all the supply chain and trade routes as well. Okay, so the concept is like this: if we somehow can predict this drop, could we have done anything to mitigate that? Now, with the help of AI, these days I don't even need to write code. I simply just put in this data. This is my predictant. Then I start to feed it all the information I showed earlier, from ocean heat content, from Eastern Pacific to Western Pacific to near Thailand, in the Gulf of India, for example. I also feed in soil moisture 6 months ago, 9 months ago, 3 months ago, something like that. Then I just feed in some neural network models. Now you're seeing here all the different colors. All this shows the lighter color means a simple model, simple statistical model, and these are more complicated AI models. So you can see that AI models can actually predict the drop about 6 months ahead. Okay. Now there's a side story here. It looks like AI is something new, right? It is not. This neural network concept was invented in 1943. Now, if you remember, the first computer wasn't introduced until 1945. So there wasn't any capability for them to calculate something this fast. The computer and the numerical methodology of neural network, artificial neural network, is basically mathematics equations trying to simulate how our brain thinks. It will start to advance more in the 1970s. Then it got stuck because it becomes too convoluted, too complicated. There wasn't enough computing power to catch up. But then, especially today, the the GPUs enable complex algorithms. Then they can transform neural network into something like a convolutional neural network. It is something that mimics not only our brain, but our eyes, our vision, and pattern recognitions, and then produce something that can mimic human logic. Okay, so again, we call this AI, but the concept was done so long ago, almost 80 years ago, more than 80 years ago, and only today with the GPU power and with the computer interface that I can do this kind of calculation using my phone. So back to this concept, if we could provide information of this drop or this drought, because we predict the drought, and the drought information help us to predict the cassava yield drop. Can any of the companies, the mills that takes the cassava to produce starch, do anything about it? So I have a visit to 3 companies alongside with Kasasa University teachers, professors, and I was told that there are many ways you can do it, from community to economics, pricing, to just trade. You just buy starch from somewhere else in advance. You can maintain your profit. A lot can be done. So when everyone else fail and you didn't fail, well, that means you make profit as well during a harsh year. So it's just one simple, very straightforward example about how AI can work. But it's not enough. Just like back in Louis Patterson's story, in 1922, he didn't have good computer. He didn't have good observation. So the second question is observation. We know weather is important, right? Now, I took this photo from Sakanakon in northern Thailand. How many stations do you think are here? None, really. So how can we get accurate weather information, right? Let alone soil moisture. But what if I tell you that we actually have such data, and we can access information of weather and climate everywhere? And that is reality. So I want to introduce you this kind of data set that allow you to tap into climate information anywhere from your office, from your home. You don't really need to go there and collect data. That is called global data reanalysis data. Because all the climate data was collected by many different ways: aircraft, balloon, stations, ships, radar, right, satellites. And to put this information into one set is not something anyone or any company can do. It takes national effort. So I want to fast forward just to show you this demonstration study. This is it is published in 1985, and in this concept called data assimilation. So they show this African continent with all the surface station and ship stations of winds. You see nothing here, nothing here. But through data assimilation, now we can produce a very comprehensive and complete weather pattern or wind patterns from almost nothing. But it's not actually nothing. It is the data, and assimilation means you assimilate into the physics how the Earth's climate system works. Okay, it's just like ChatGPT interpreting your incomplete sentence, and you can get something. Sometimes it's right, most of times, but although that's not always right. But how do we know that we are seeing this cyclone here produced from nowhere is true? At the time, 1985, they used satellite image and they found this swirling sandstorm, which is well captured by this computer system without having data here. Okay, so that's remarkable. That means that if you generate this data for a long time, you can actually study this area's climate change without having the actual observation, which you never get anyway. So it's the best educated guess. Now, this was 1985. Today, most of the reanalysis data incorporate satellite observation as well. So they can produce very fine resolution, many fine details of map everywhere around the world. And these data sets are mostly kept not as a secret, but as a very specialized tool for researchers like me. But I think that the industries should really use that. One of the reasons is that it can improve our understanding of weather. Now, having spent a year in Thailand visiting around, I was frequently asked, like, why, and especially people who have spent time in middle latitude countries, Korea, Japan, Canada, or Europe, they say that, oh, you know, when I was in Wisconsin, USA, the weather forecast was pretty accurate. Why now in Thailand it is not? So I want to show you something to explain that. Okay, now you see this is a cloud image, and you can see that in the north. Okay, I cannot really show you that, but it's okay. You can see the northern part. The northern part, you can see that the weather system moves. Okay, look at North America, for example, or look at Russia. You see there's a hook-like cloud moving. So those are systematic clouds. But how about Thailand? How about Thailand? If you can lock your eyes on Thailand, you can see that the clouds just pop up like that. It doesn't move. The challenge is that we know it's very moist and it will rain, most likely rain. We just don't know where it will rain. Okay, so it's because the clouds are very small compared to larger scale climate. And this is one example of a project I have done for the US military, where we were trying to forecast Texas extreme flood risk beyond 2 years. And this is Texas. So because we know this linkage that the ocean, the same pattern that affect Thailand's soil moisture, also affect Texas as well in similar ways, but different season, right? But to really understand flood risk, we need to understand cloud. So floods almost always produced by thunderstorms like this. You can see that. And for global models, which we need to reduce the resolution, we need to simplify it in order to run fast enough. It doesn't capture something like that. So we need to run a different model to capture details like this, okay? And that's how we did. And this technology is very mature now. It is called downscaling. It basically helps you find the details embedded in the climate signal. So we have proposed to build a database for Thailand, and we can apply that to Southeast Asia as well. The concept looks like this. The reanalysis data might give you this kind of grid point. Then we can use statistics or computer models to generate even finer scale like that. So hopefully, not hopefully, we aim to produce data for different time scale. And then for many different variables, especially important, those are important to agriculture productions like this, okay? And we can provide them at the fingerprint, and, using your phone only at all locations for both future and the past. Future means forecast, for the past. And now with the AI interface, we no longer really need to build complicated interface like this. These are for experts. These are for people who have gotten the degrees and went through the same training like me. But for everyday users, we can have the easy to use and updated, also chart supported data archive. You don't really need to click anything or understand anything. You just need to ask questions and to get answers. So here is a demo to show you how this can be done, which is previously unimaginable. Let's just say this is something I presented in the beginning, back in June, when I was given that talk at the machinery workshop. And at the time it was June, so I was asking how the September precipitation would be for Northeast Thailand, okay? And this is a demo of a ChatGPT plugin concept. So I asked it what the precipitation will be 3 months in the future. And you can see that ChatGPT gave me a response in a quantitative way, saying that it will have slightly above normal rainfall. And I asked, well, please be quantitative, right? And then because I'm a meteorologist, I know the data set, I know the data source. So I specifically asked for 2 data sources. If you are everyday user, you don't need to do that. But then you come out with 10 to 20% above normal versus a different data set, 15 to 25% increase in precipitation above normal. Okay. Now imagine this was done in June, asking about September. Today we are in October, so we can actually test if this information is correct. And by the way, these were the information web page that ChatGPT got it from. Now, if you are an untrained person, if you're not a meteorologist, there's no way you can understand all this information. But somehow ChatGPT can read this map and tell you the information. And then you can see this is observation map. Now this looks very complicated, but let's focus on here. Northern Thailand, what do we see? We see a little bit of a green and blue colors, which means above normal precipitation, around 20%. So this was quite accurate. It is something like, just like your weather forecasting, you bring out your phone, you ask for weather at your location in the next 5 days. We can do that for the next month and next season. It may not be always accurate, but it will be updated, and the forecast will usually become better as they near. So it helps you plan. And for agriculture, this becomes very important. So I used to teach a course called data analysis, climate data analysis, that involved a lot of coding